In today's video, we're going to go over the difference of rational and irrational numbers. So all numbers on a number line are real numbers. This includes positive and negative numbers, fractions, decimals, square roots, cube roots, pi, as well as rational and irrational numbers. Some important subsets of real numbers are natural numbers. Those are the numbers that you count with, 1, 2, 3, 4, 5, and so on. Whole numbers are the counting numbers and 0. So we include 0 with our whole numbers. Integers are positive and negative whole numbers, including 0. So you can see the examples of integers here. Rational numbers are any number that can be written as a fraction. So that would be a ratio of two numbers. And then irrational numbers are non-terminating. That means it's never ending. Non-repeating, so it doesn't repeat. Decimals, and radicals that cannot be simplified. Something like the square root of 2. This is what our real numbers consist of, are these things right here. So you've talked about this a lot in previous years. What I would like you to do is take a minute and pause this video and see if you can classify these numbers here as rational or irrational, and then see how you do when I go over them. So on example A, we have 7.84 with a bar on top. That bar tells us that 0.84 is repeating, and it says irrational numbers are never ending and non-repeating. This one is repeating, so this one is rational. We can write this as a fraction. On B, I have 10 divided by 3. This is a rational number because it's written as a fraction. Remember that rational numbers are any number that can be written as a fraction. The square root of 12. Well, 12 is not a perfect square. And if I try to do birthday cake with 12, let's see what happens. I have a pair of 3s or 2s that can leave the square root symbol. And 3 doesn't have a pair, so 3 stays inside. That's as simplified as that's going to get. I still have a square root as a part of my answer. So because I have a radical that cannot be simplified, because I cannot simplify the square root of 3, that would make this number irrational. For example, D, I have 10.375. This is a rational number because I could write this as a fraction. So I have the number 10, and then remember your decimals, this is the tenths, hundredths, and thousandths, so that would be 375 over 1,000. So because this number can be written as a fraction, that makes it rational. The square root of 256 is 16. 256 is a perfect square. So because my answer is 16, 16 is a rational number. I can write 16 as a fraction by saying it is 16 over 1. For example F, I have 0.25. This can be written as a fraction as 1/4. So because it can be written as a fraction, that makes this a rational number. Pi is probably the most famous irrational number because it is never ending and it never repeats. The square root of 2 cannot be simplified, so this is also an irrational number. If you try to do birthday cake, you don't have any pairs, so you can't simplify any further. So this is an irrational number. Then we have a couple of examples that say, are the following numbers rational or irrational? Well, let's see. The square root of 9 plus the square root of 4. Well, the square root of 9 is 3. And the square root of 4 is 2. 3 plus 2 is 5. 5 is a rational number because it can be written as a fraction. So rational would be our answer. On example 2, I have the square root of 100 minus the square root of 2. Well, the square root of 100 is 10. If I try to simplify the square root of 2 by doing the birthday cake method, I don't have any pairs. And so that can't simplify any further. Because my answer still includes a radical that cannot be simplified, that would make this an irrational number. For example 3, I have the square root of 8 plus the square root of 49. If I do birthday cake for 8, the smallest prime number that goes into 8 is 2. 2 goes into 8 4 times. The smallest prime number that goes into 4 is 2. 2 goes into 4 2 times. The smallest prime number that goes into 2 is 2. 2 goes into 2 1 time. When you get to 1, you're done. This is the candle to your cake. I am looking for pairs of numbers to be able to leave the square root symbol. Here I have a pair of 2's that can leave. This 2 does not have a pair, so that 2 is going to stay inside my square root symbol. Plus, the square root of 49 is 7. Because my answer still includes a radical that cannot be simplified any further, that means that this is an irrational number because it still contains a square root that cannot be simplified. And then lastly, let's look at example 4. The square root of 144 is 12. And then if I try to simplify the square root of 15, the smallest prime number that goes into 15 is 3. 3 goes into 15 5 times. The smallest prime number that goes into 5 is 5. 5 goes into itself 1 time. When you get to 1, you're done. That's the candle to your cake. I don't have any pairs here. So that means that the square root of 15 is as simplified as it's going to get. Because my answer still includes a radical that cannot be simplified, that means that this would be irrational.